Hi.
Hello, good morning.
Hi, Jen.
Hi, Peng. Hi, Benayak. Yes, I think the other session just
It just finished, yes.
finished. So
I think we should give them a few minutes.
give a couple of minutes maybe. Hi,
Yeah.
Peng. It's
Yeah, hi, Jane. Nice to meet you.
Nice to meet you. I didn't get a chance to meet with you, but in the previous talk they did mention about your name.
I was very nervous.
Yeah.
Hey.
Let's see. Okay, the number is, let me see if Jordan is here as well.
I'm here.
Can you actually make me host, Jordan, so I can actually make anyone else host if needed? Because right now I don't have
Let me
permission.
try. I'm hoping
Okay.
it won't mess up the live stream.
Okay. If not, you should make Jun. Okay, if you could just make Jun a co-host as well.
Yeah,
just
I
so
can
that
certainly. Let's see.
maybe make Jun and Arman co-hosts, and then we don't have to worry about breakpoints.
I'm actually not seeing that option. So
Yeah,
I'm-
I couldn't see it myself either. Let me just try one more time. Allow to record, mute. But I guess Doug is a co-host and he is around, so I feel
Okay.
that
Yeah,
should-
I'm a
it should be
co-host, but I
fine.
also can't add anyone else as a host.
Yeah.
Okay.
but yeah, I'll be here too to
We
help.
think
Okay.
Jordan can.
Any
Okay.
issues.
That'd be great.
Cool.
Yeah, Jordan can take care of the YouTube, right?
Yeah, I can copy things from YouTube into the chat.
Thank
I'm happy
you.
to do that.
Okay. Maybe we should start. Is Arman here? Arman is.
Yes, I think he is.
Yep, I'm here. Yeah, feel free to start,
Sorry.
Jen.
I replied sure to everyone. Sorry, Arman. The sure was to you. So.
All right.
Amin is in California time zone, so it's really difficult for him.
Mhm.
All right. Okay.
It's not only me, it's also Pong. Really appreciate Pong being here. Thanks, Pong.
Yeah.
Yeah, it's a little early for me, but it's okay.
Okay, so let's get started. So welcome everyone. Kai, will I be able to share my screen?
It should. Let's see. Do we need? Let me
You
just
should
try
be
that
able
as well.
to go ahead and
Don't
try.
show-
Should be fine.
Okay, do you see that?
Yeah, see it.
Okay, wonderful. Yes. Okay, great. Okay, let's start. Again, welcome everyone. It's my great pleasure to chair this panel discussion session. And we have so many wonderful speakers and then seminars. So the discussion is basically to provide our little bit reflections and discussions. We will have 4 graded panelists. Let me briefly introduce each of them. So Dr. Peng Ding is from the Department of Statistics at UC Berkeley. I understand his area is specifically in causal inference. Then the other panelists are from our own program. So Professor Chuanhai Liu, and then I guess we'll provide some discussions and then comments on this seminar topics. Nianqiao Xu is a new assistant professor, and then we're very pleased to have her. Fei Yue is also a new assistant professor, will join us for the panel discussion. We also have 2 moderators, Vinayak Rao and then Arman Sabagi. I guess all of us I'm very pleased to have them to organize this causal workshop over the summer, and again organize this part of the organization committee for this seminar. So welcome all of you. Let me just take this advantage to briefly talk about my thinking or reflection of this seminar after this seminar series. So this is actually a great time to rethink causal inference. As you can see from all of the speakers, it is not in the past years, several decades for statistics, it is not very the mainstream. But with randomized control controlled trial, a causal inference can be done through the estimation of treatment effect. So all of us pretty much have some knowledge or experience of doing estimation. So I think this could be an area many of us could recall our expertise and then possibly contribute. At least some of them, for example, regression-based or non-parametric or even machine learning approach. And again, hypothesis testing, that will be a strength for all statisticians. I also list some of my own experience in doing issues related to confounding factors and how do we handle them. So this actually is maybe the most challenging part when you have observational study or many other experiments that the two groups are not randomized with respect to confounders. So we did actually a work back to, a little bit 15 years ago for estimation and test of survival functions. So we did a adjusted Kaplan-Meier estimate, which is a try to handle confounding factors, which I find it is a connection with the topics we heard over the last 4 seminar series. So it's a recall for my previous work. Okay, so with that, let me pass this to the first panelist, Dr. Peng Ding. So that's your floor, please.
Okay, sorry, I didn't prepare slides because I didn't realize we need to prepare slides. Yeah, I watched the seminar series last night and also this morning from Peter. The 4 speakers were Don Rubin, Jimmy Robbins, Julia Pearl, and Peter Billman. And 4 of them came from quite different background. Don was from more applied perspective of statistics and causal inference, and Jimmy is from more theoretical, although Jimmy has a medical doctor degree. Julia is from the computer science perspective. He focused more on the computer science theory of causal inference. And Peter is from more theoretical statistics and machine learning perspective for causal inference. I was a student of Don in graduate school, although later I also worked a little bit with Jimmy, jointly with Tyler Vanderweel. So I have papers with the first 2 speakers. Yeah, my training was also a traditional perspective, like as Arman was introducing the Fisherian and Neyman perspective, thinking about causal inference based on randomized trial and how do we make inference based on randomized trials. In those problems, the causal questions were very well defined. We have well-defined intervention, treatment control, well-defined potential outcomes, and randomized trial. How do we make inference? How do we make robust inference without making strong modeling assumption? That's one area I was working on, like how do we do randomization-based inference? Also, borrowing some modeling strategy, but we don't really believe those models. Like we call it model-assisted causal inference. It's more like non-parametric or robust statistics, but from a randomization perspective, not the traditional like kernel or spline perspectives. And Jimmy Robbins' focus was slightly different. He was focusing on more complex longitudinal studies with non-randomized treatment, where he proposed his method called G computation. In some sense, it's an extension of the Rosenbaum-Rubin results on propensity score and those results for point treatment. Jimmy's focus is the time varying treatment, which involves a lot of technical issues. For example, if we have time varying treatment, we also have time varying confounders. How do we control for those confounders? Because those confounders are, on one hand, they're confounders for the outcome. On the other hand, they're also post-treatment. So they're also part of the outcome. The adjustment of those time varying covariates are very difficult. And is still a very active area in causal inference because we still don't know how to make those methods robust and stable in numeric analysis. And Julia Pearl's work is really inspiring. Especially, I think I learned causal inference first from Julia's book before going to graduate school. When I was in college, I read his book, but it's really a very dense but interesting book. His causality book was actually very ambitious, saying, okay, how do we think about causality from a more systematic way? Like we imagine there is a graphic model describing the causal relationships. Although a lot of people criticize this framework, saying, okay, where does that graph come from? That's another fundamental challenge of causal inference with graphs. But at least his language, his causal graphs provide a formal language to think about causal relationships, especially for problems with latent variables. Like we cannot measure all variables. In those cases, how can it be possible to identify causal effects? He has the famous backdoor criteria. The backdoor criteria basically recovers the Rosenbaum-Rubin results. The mathematical language is different, but the final formula is the same as Rosenbaum-Rubin formula under ignorability. But he has a new result called the front door criteria. That's unknown to statisticians. That's really another interesting thing, saying even if we cannot observe all unmeasured confounder, if the graph has a particular structure, we can still make some progress. There are not that many applications of front door criteria, but it's very interesting result. At least statisticians didn't know that. And he also have other discussions like probability of causation, because the Rubin or the Neyman-Rubin perspective, as I was mentioning, focus on the well-defined treatment. We have a treatment, we have an outcome. What is the causal relationship? Or what is the causal effect of that treatment on the outcome? But Julia was thinking about other problems. For example, when we see the outcome, we ask, what is the probability that this outcome is caused by the treatment? It's like the reverse problem. So he called it cause of effect versus effect of cause. Okay, so the Neyman-Rubin framework is effect of cause. Evaluate the effect of a particular treatment, and Julia also discussed what is the cause of the effect. And moreover, the causal discovery literature is even more ambitious. So if we have a observed data set, can we recover the causal mechanism among them? This sounds like science fiction, because if we have two variables, X and Y, how can we infer whether X causes Y or Y causes X? That seems impossible. Like we have scatter plots of X versus Y and Y versus X. There's no way for us to figure out the direction unless we impose some other strong assumptions. Like these things cannot be assumption free, and oftentimes assumptions are very strong. And Peter's talk is quite different. His talk is similar to the econometric, like he cited Habermas econometric perspective, and also the John Tukey perspective about stability and the causal effect. I haven't paid enough attention in the past few years to Peter's work, although I know it's a lot of exciting research has been done by him. I'm more familiar with the first three. That's why I comment more on them. So I will stop here.
All right, let's move on to Chuanhai.
Hello. Can I share my screen? Hello.
Yeah, you can give a try. On the bottom, there's a share screen green icon. Can you see that on the bottom? Maybe you want to give a try. It should be.
Where is that?
On the bottom.
Share screen?
Yeah.
No, I cannot see it.
Should be a green arrow on the bottom.
You might have to click Zoom first.
Oh. Okay. Okay.
You don't have that? You don't have the menu list?
Now I can share desktop. Oh, see. Okay,
Yeah, give a try.
Yep, we can see it.
good. Okay.
Yes.
First, thank you for inviting me to be on the panel. Is probably the decision was based on prior information because I was a former student of Dan Rubin. But the reality is that I've never done any work on causal inference. So I really don't much to say about causal inference. But you want to say something, I prepared a few slides. So what I can do is that what is the causal inference should I care? In practice, when you do modeling, no matter what is formal causal inference or not, we always have the informal causal reasoning. But to be serious on causal inference, so let me take one step to thinking about what it is. So my starting point would be starting from when you do not know anything about it, you look from a very high level. So what is a science? What is belief, which concerns about knowledge? Then what is statistics? That's the one thing I thought about it. Because in causal inference, you do have to be serious as a scientist. So what do you mean by science? Well, you can look at dictionary. The two keywords I think are important. Basically, you do applied work. You deal with real data, and important for making causal inference, you really need to think about experimentation. So that's my understanding. So now what is statistics? You're thinking about statistics. Statistics basically is concerning about how to convert those experience, which I call experience, data, observations, and subject matter into a formal knowledge. Knowledge basically you describe it as uncertainty quantification on problem of interest. So that's my understanding of science and statistics. So now the next thing is, does that have anything to do with causal inference? Of course. Causal has a lot to do with all the general area of statistics, including application, or sometimes we call it applied statistics. Theory, this theory I'm talking about the theoretical framework, not mathematics. And the computation, because in statistics you want to see the real numbers, not just formulas, which is just that simple. To be more specific, I wonder if you really want a series about causal inference or a series about the statistics or science in general, we are really facing important unsolved fundamental problems. For example, in the area of application, everybody can talk about the model building, right? The question is that what is the general theory for model building, toward solving scientific problems? In theory, and especially, as we know that that's a fundamental problem for valid and efficient inference. The reason I'm talking about that is because when you do causal inference, you really have to be objective, at least try to less subjective. So thinking about that, so if you're thinking hard, you will find that if you're thinking deeper, you'll find it very difficult. But that's something we really, statisticians do have to consider. The next one, of course, everybody knows that we are still far away from computational and desired computational methods, that is, finding the global optima, even in the deep learning. So I can say a lot about that. I have a private conversation with Xiao Wang and Michael Zhu in the department about this. There's still a lot of work to do, I guess. Okay, having said that, well, this provides, now how can I make a comment on causal inference? The first thing I want to do, because causal inference is a challenging problem for me, it's fundamental. So I will use what I call a high-level 3-step process, which I think is important to for tackling challenging statistical problems. So first, got it right, which means valid. That makes sense. Then you make a incremental progress. So in the end, when we say a problem is solved, which means you can do it best. So I will use this one to provide my naive view of causal inference. So causal inference, so first thing is you want to establish a causal effect to some, the cause of some effect. Well, to be a person who is subjective or conservative, certainly he would agree with this slogan. Put it here, is that clear? Can you see it? It's too small. Basically,
Yep.
it's elaborated in a paper by Holland, JASA paper in 1986. So the slogan is due to Don Rubin, called no causation without manipulation. That's exactly what I would agree. I think is key to understand causation. Otherwise, you have no objective reason to claim causal effect. So, well, from the observational study, you can do that, but you are thinking about the nature is doing manipulation. But problem is that you have to figure out how the nature, the manipulation, which you in the context of controlled experiments, what's the distribution of the assignments and how that distribution is related to unobserved variables that potentially has an effect on outcome. So that's the beauty. You cannot really do that if we're thinking about that deeper. But only thing you can do, that's the beauty of so-called randomization. Well, you can generalize that with some mechanism as long as the mechanism does not involve any confounding effects. So that's what I'm saying. That's what my understanding for Rubin's framework or early based on randomization, which is due to or Fisher or Lehman. Mathematically, the beauty is that it really integrates out observed, both observed and unobserved variables. So that's in the observational study, you cannot really do that. Well, you can do, say, use a propensity score to control, hopefully, on the observed quantity, but you will never able to control over the unobserved one. So you take a lot of assumptions, which you have to think thinking about the well, in Peter's word is probably robustly. I think fundamentally it's different. Anyway, that's a difficult. Well, another one, James Robbins. Well, according to the, I look at his Wikipedia. He said, well, it's related to Julie Pierce. So I spent some time because I don't know anything about really anything about the causal inference. So I read his. I didn't have time to read his book. I read one of his papers for statisticians. So my understanding and books look. I didn't really find anything new except that it's from computational perspective or a based in formulation, or he called it mathematical formulation of things are familiar. So I'm not saying it's not, I mean, of course it's inspiring. So I'm trying to thinking about deeply what's new. And so I probably have to read more to really understand it. So I probably have said too much. That's my misunderstanding. Okay. So in the end, I will say to myself, there's still too much for me to learn. Thank you.
Great. Okay, we move on to Nian Chao.
Hi everyone. I don't have slides.
Hi, can you stop sharing?
Oh, of course. Let's see.
Well, I quite agree with there's still too much to learn.
Yes.
That's what I'm going to talk about actually.
Well, okay. Oh, stop sharing.
Yeah.
Sorry about that.
Yeah, go ahead, Nian Chao.
Yeah. So thanks for giving me the chance to share my perspectives on our very successful seminar series. And I also think quite similar to Chuan Hai, the reason why I got invited to be a panelist was because like Peng and Chuan Hai, we all studied at Harvard Statistics. And there's a stereotype that if you got your degree from Harvard Statistics, you must know something about causal inference. And in my specific case, that is only, I think, like partially true because I allowed myself to stop thinking seriously about causal inference the minute I learned that I passed my qualifying exam. So, so I really appreciate our seminar series, which allowed me a chance to rethink about important concepts in statistics with both a theoretical and a historical perspective. And I have to admit that I took a very myopic view while watching the seminar series, which means that when I was watching or learning from our speakers, I just cannot help thinking about, oh, what does this mean to my own research projects? So I think like in a few minutes I'm gonna have, I'll just share about the questions that intrigued me to think about from learning from these seminar series. And so I'll just be very brief and talk about 2 points. But in order to do that, I first need to talk about the research I do. So there are 2 main themes of research. The first one is Monte Carlo methods, which is very useful when we have a concrete objective like to optimize a function or to approximate some integral. And the second theme, which I think is more relevant to today's topic, is agent-based models, where I study a complex system in which there are a lot of agents or individuals that interact with each other and with the environment. And I think interaction is what leads to the connection I'm thinking about. So the first question I have is about interference. So there was actually a question posted, I think, from YouTube during Julia Pearl's talk, asking about, is there a fourth level of counterfactual models where I would not only think about treating myself, but also what a treatment or control on another person that might interfere with my actions. And so because I study interactions, and I think at that moment I realized, oh, so the interactions that I have been interacting with in my research are actually interference if I have to think about them in a causal inference context. And so as a result, I just drew the graphical model I would have in my research, and then think about, oh, what would like Y be? What would be like the result of my whether or not I get a disease, given that I do vaccination. And if I have to think about this in like a network and like social interactions context, I think that this question I have doesn't satisfy the backdoor condition, which means that I cannot estimate the probability that I'm gonna catch coronavirus, given that I do vaccination. And I think as James Robbins correctly pointed out in his talk, this is very hard to do, and it is actually this kind of interference is intractable. It's an intractable problem, but I was like fascinated and intrigued by this kind of discussion, and it gets me start thinking about, oh, what does interference and interactions do in the context of an agent-based model or the joint evolution of a complex system? Okay, that was point one. And a second point was, I think this is not mentioned in any of the talks, which I started to think about the contrast or the connection between individual level treatment effects and population or group level treatment effects. In the context of infectious disease, this would mean what? Okay, so maybe Y in this case would be whether there's gonna be an outbreak or how many people will be infected as a result of an outbreak. And then the X can be whether I get the vaccine. So, and then so like the treatment. So what this means in the agent-based models context is that all the treatments we have are on an individual level. We can only give a treatment to each individual. But the effect that we would like to observe is actually on a population level, whether a whole population develops an outbreak. And I think, so I've been thinking about how to resolve this contrast between individual level treatments and the population level effects that we would eventually like to observe or to measure. And I think I quite agree with Chuanhan in that there's still a lot to learn, and I will be interested in the future to think more about how either the potential outcome framework or the graphical models framework would mean in the context of individual and population level treatment and effects. Yeah, that's my 2 cents.
Great, thank you. Next, let's move on to Faye.
I'm really honored to be a panelist in this panel discussion, and I agree with Nianqiao and Chuanhan. There are a lot to learn for me. Yeah, I don't think I'm expert in causal inference, but I'm always interested in it. So I really like this seminar series. I think I learned a lot, and especially get a better understanding of counterfactual framework, potential outcomes, structured causal models, and some intervention, and the difference between an intervention and association, a statistical association. And also I first learned causal inference also from Judy's book, the causality book, and also learned from Peng's Chinese articles. First learned causal inference, yeah. And our speakers also discussed some very active areas in causal inference, like unmeasured confoundings, and integrate machine learning and artificial intelligence with causal inference, like using transfer learning ideas, use other the relationship, the effects from other some source population to get a causal inference in the target population. That's my basic understanding. And the relationship with causal inference with some robustness, distribution robustness. And personally for me, I also have some causal related projects, like with considering estimating causal effects for multivariant outcomes, also based on randomized trials. And I've also done mediation projects for high-dimensional mediations, and we consider heterogeneous causal effects. So, and that's related to like personalized medicine. So I have another project related to personalized medicine, but in that one, we have not considered it from a causal perspective, but we do have a treatment and some outcome, and we want to recommend the best treatment for each subject based on some like covariance, some like demographic covariance of each subject. So yeah, that's my brief comments on the series. Yeah.
Okay, thank you, Fei. So let me pass this to Armand and Vinayak. You guys can maybe moderate with questions, or we can also open for general audience for discussion and questions.
Yeah, so I guess if people have questions, they should definitely post them on the chat. Okay, maybe I can ask a couple of questions while we get started. I think one thing that I was interested in, so I'm not an expert in causal inference, but I kind of know that really there are kind of two schools of causal inference: the Judea-Pearl school and the Rubin kind of approach. And I think this is maybe kind of a bias from a statistics viewpoint. We know, for instance, that econometricians do a lot of causal inference as well. So I'm just curious how their methods. So I guess Peter Bowman did mention econometrics briefly. I'm curious whether they have their own framework, or their frameworks reduced to kind of hybrids or special cases of Pearl's or Rubin's model, or I guess maybe even bioinformatics or other kind of scientific disciplines where people are asking causal questions and they have their own ad hoc procedures or maybe their own rigorous procedures in their special niche to solve these problems. I don't know if any of our panelists have any comments on causal inference outside these two kind of frameworks that we have been discussing in this session, in this series. Anyone wants to volunteer an answer?
Okay, maybe I can say something.
Mm-hmm.
I think initially the fields were going together, but later they diverged.
Mm-hmm.
Like in Peter Bowman's talk, he cited Habermas' paper. Actually, if you read Habermas' Nobel Prize talk, he actually mentioned the influence of Neyman on his research, because he was actually visiting Neyman for some time. So he mentioned the influence from statisticians. That's the econometric, one of the econometric perspective. And other econometrics, for example, instrumental variable is quite important tool for causal inference in econometrics. That's one of their own subfield.
Mm-hmm.
I remember Jerry Hausman wrote an article saying in most cases, econometricians borrow something from statistics and develop for their purpose, but for instrumental variable, it's really from econometrics itself. That's really their own thing. But actually, if you go back to the origin of instrumental variable, you will find these are from both econometrics and genetics, because the first paper was written by father and son. So the father was a Harvard economist, and the son was the genetics expert later. So it's I'm not an expert on genetics, but I guess some people heard of the name like Civil White.
Civil White, yes.
Yeah, I think he and his father first wrote an article. Later it becomes the idea of instrumental variable. And later it seems statisticians lost interest for causal inference for a while, but there's still some research like Kornfeld, Cochran, and later Don Rubin, but causal inference was not the main thing in statistics. still very important in econometrics and genetics. So for me, they're actually the same. But for a while, they diverged a little bit. If you go back to the root, you can find the commonality. Yeah. I think when I was reading the Jiang Tuqi article, I think in his, at least in his references, these things are mixed together. Yeah. Okay, that's all my comments.
And maybe I guess another hope for this series was to kind of maybe help people understand different languages from different frameworks. I think at least in my mind, it's not as clear. I guess also listening to other people, there was still, for instance, is a counterfactual in Judea-Pearl. So Judea-Pearl has this hierarchy of observation, intervention, counterfactuals. So is that basically the same as a potential outcome in the Rubin's model? And I remember reading, for instance, in Gelman's blog, that he does not think the do operator makes sense. I don't know if anyone has any insight into why Gelman might say that, or maybe what the sources of disagreements are among these different causal frameworks. Maybe this might be best aimed at maybe students of Don Rubin, who what they think of Judea. Maybe another way to ask is what do people who work with Don Rubin think of Judea-Pearl's framework? Maybe theoretically, usefully, and how it's different from. Yeah. I think John Hai did mention briefly about this, but any other comments are welcome. Let's see.
Okay. Hello. I can elaborate a little bit. Again, I know nothing about causal inference. Well, you take one step back. What's the scientific problem you're trying to solve? Can you hear me? So take one step thinking about what a scientific problem is. But even, if your research is coming from real design experiments, you feel more confident about your conclusion. Say from observational study or observational data, both of them are, even you got, to me, they are just conjectures. And that's what Peter said. Well, really, what you have to do is to go back to redo the experiment with the current subjective results with the guidance. So everything has to be tested eventually by going back to the real world. That's my reaction. Don't think too much about the mathematical details. Thinking about the real problem, thinking about if you really want to do theoretical work, my personal view, even I say very loudly, is the formal inference that makes sense, scientific sense. So if you read the articles, the books, you see people make arguments, circling arguments, making it very difficult to read nowadays. Nowadays you sit and you have a mask and sit in a tiny space. It's very difficult. Okay, I can only say that. Thank you.
Anyone else has anything to say? And again, anyone has questions, please hand them in. Otherwise, I'll just be asking my questions or adding in my comments over here. Let's see. Any questions yet? Not that I can see. Maybe here's another thing that I wanted to mention that I'm curious what thoughts people have, and I guess it relates to the comments on your own research as well. So I think one aspect of these series and these workshops was machine learning and causal inference. And I think a lot of the machine learning has just been used something like neural networks or decision trees or something in some sort of imputation part of your causal inference algorithm, right? So you just use the predictive power of machine learning to help you do causal inference. But I think Peter Bowman's talk was interesting because it kind of showed how causal inference can also help machine learning tasks. And for instance, another example would be, for instance, fairness. So that's something that people in machine learning are very interested in. And there has been work on using causal inference to kind of formalize fairness. For instance, so what is fairness? I have some prediction task or some regression task. I want to predict y from x, but there are some attributes of x that are protected, right? Maybe I don't want my predictions to be based on gender or race or something like that, right? So that's kind of what fairness tries to do informally. And now you can't just solve this problem by just dropping those attributes, because those attributes might be correlated with other attributes. So it's not a simple question of dropping covariance. It actually becomes a formal. To formalize this, you can use causal inference. You want to say, if I go back in time and change the value of these protected attributes, I want my predictions to be unchanged. Right? And that's how you can kind of formalize fairness using the language of causal inference. So I don't know if people have other applications, or not just in statistics, not just in machine learning, but statistics, where ideas from causal inference can kind of help you revisit these problems and rethink these problems. And maybe even if you're not fundamentally interested in solving causal inference problems, can these tools help you with your own research? Any?
Can I say a few words?
Sure.
Okay, so first of all, I don't know causal inference. I do not do research at all, but I was interested in the Julia-Pearl system a few years back. And so I just tried to understand the thought process. And from my understanding, I believe Julia-Pearl is not infer causality. He's assuming causality given by the DAG. And based on that, he developed a very, very intriguing system to assess, sort of quantitatively assess the confounding effect. So his first principle was that causality cannot be inferred from observational data. So causality itself comes from somewhere else, but he provided the thought process to quantify the confounding effect. Of course, confounding is a very general term. And he defines what is intervention and what is mediation and things like that. And so I didn't read anything about the Rubin school. I only tried to understand the thought process of Julia-Pearl's sort of system. It's a very intriguing system, and it's logically coherent, I believe. But itself does not address inference. It does not address estimation. It just assumes that you do have those quantities ready, then how to quantify the sort of a confounding effect. And to fill the component, you need other tools to estimate things. And actually, I did prepare a set of notes, very brief. And if anyone's interested in learning the basics, I think I can share that. But that was no deep research or involvement or anything. It's just try to figure out the ABC of the Julia-Pearl sort of thought process. He's got a very coherent system.
Mm-hmm. Yeah, thanks for those comments, Chang. Any comment from the panelists on? But there is a question also. Before I move on to the next question, let me just pause for a minute.
Yeah, I agree with the summary of Julia's work. Like, he was not that ambitious, saying we should build the DAG from the data. Maybe in his early stage, he was interested in that. But in his later book, I don't think he focused on too much on that perspective. He would rather say, okay, causal DAG knowledge is like something beyond the data or before the data. Like it's helpful for us to make sense of the data. Like if the DAG is only partially observed, how can we, or is it possible for us to identify the causal effects? That's why he usually talk about identification of causal effects. I don't think statistics is interesting to him. He never touch any data to analyze data, like to estimate causal effects. I don't think statistics is interesting to him.
Mhm.
He was interested in a higher level question, in whether causal inference is possible. Like if you give him the joint distribution of the observed data, and he has a DAG, and based on these two pieces of knowledge, can we say anything about causal effects? I think that's all his focus. Yeah.
Mhm. But so doesn't, for instance, the Rubin model also require to specify a model, just like Perl has to specify a DAG? So,
the Rubin framework is more, I would say, traditional or more less ambitious framework. We only talk about the one treatment, usually binary, and there's a well-defined outcome. So we just think about their relationship instead of thinking about the whole system. Like we build a whole graph for everything. Like that type of knowledge seems too much beyond the data. Maybe for a lot of applied statisticians. Like if you look at a lot of applied problems, we don't really know how to build a DAG for all the variables, right?
Yeah, for about the DAG, so I think Peter mentioned the Markov equivalent class. My understanding, my naive understanding that based on like some conditional independence, we could get some equivalent class and get some sense of some direction from the like Markov equivalent class technique. So I'm not sure whether this is correct. This my feeling about it. Yeah.
Yeah, I think what you said is right.
About Markov class, I believe Markov class was you can implement Markov class using undirected graph, but you lose a direction. And there are certain things that cannot be represented by the Markov, like the collider.
Yeah. There are some undirected links,
Let's see. So here's a question from YouTube. I guess here's a simple question from YouTube, and maybe a useful question. What would be examples of causal inference applied in computer science or industry, or maybe some non-traditional applications from the usual ones that we have heard in these talks, which is mostly biology and economics. So any suggestions from our panelists are welcome.
I guess the obvious answer of application in industry would be A/B testing, which under Dan Rubin's framework would be, if you don't change your website, it's the control group. And if you change a button from like whatever you had before to a green button, then that's the treatment group. And if you compare a difference between, say, a yield or a click-through rate on that button, you get the average treatment effect. But that's maybe too obvious as an answer, and I'll let other panelists give their answers.
I can talk a little bit about clinical trial. Clinical trial is really just a causal inference problem, because you really want to see whether, the clinical outcome is due to the treatment or not. So, which is where we all get started from the early Dan Rubin's framework. Yes, pretty much, right now, if you talk about, vaccine for COVID, whether this is really the cause for not getting the disease, that is a causal question.
I think maybe one other application from industry that people haven't mentioned is something like reinforcement learning. For instance, you have an agent that's trying to navigate or learn an environment. And really, this is a question of learning causality in your environment, right? So I think there are a lot of people who are trying to apply reinforcement learning for various tasks, for robotics, for instance. And at some level, there are aspects of causal inference buried in all of these tasks. I don't think any speaker spoke about, I think Peter Bowman briefly spoke about self-driving cars, but I think this itself is a whole the connection between causal inference and reinforcement learning, Markov decision processes is also an interesting question, I think.
I guess another example related to both reinforcement learning and clinical trials is mobile health. Something like you send a notification to those involved in the experiment to, hey, you should exercise. And then like whether you adaptively learn whether you should send these notifications, push these notifications to the experiment units. I think that's like a big problem in mobile health and like reinforcement learning or sequential decision making. I think someone briefly mentioned this, like referring to Susan Assey and Susan Murphy's work.
Let's see, are there any other questions that I can see? No, I think
there's a long one in.
Someone just posted one.
Yeah.
So let's see. It seems that different schools of causal inference deal with estimands differently. For instance, in the Rubin causal model, the estimand is based on the treatment variable of interest and is defined first. Whereas in some areas like causal discovery, perhaps the estimand is something to identify first. Does this indicate that there are two or more different classes of causal problems? Anyone wants to comment on this? I think at a high level, maybe before anyone answers, I think this relates also to Peng's question, which is, are you interested in, and also what Chong's comments, which is, are you interested in estimating something, or are you interested in just specifying the causal structure? But I don't know if anyone else has any comments to elaborate on this. Right? Or just learning whether you specify your DAG or you try to learn your DAG. These are all, I guess, different classes of causal problems. I don't know if there's any others that someone would like to comment on.
Yeah, I agree with the summary. These are two types of questions. Actually, questions in two directions. Right? One is define the cause first. The other is to infer the cause. So I think they are different problems. I think there was a review paper by Andrew Gellman. He was reviewing several causal inference books. He just classified the problems into these two categories. I can find the link to the article.
That would be useful. Let's see. I think we are basically out of time right now. I don't know if anyone wants to add any last words or.
May I?
Oh yes, Dennis, please do that.
Yeah. First of all, I think this is a really successful series. You can't expect better speaker than what we have in this program. All four speakers are really a leading researcher. Plus, at the beginning, Amin gave a wonderful introduction type of lecture that also helped. So those are all quite impressive. Today's discussion also quite impressive. I mean, at least we exchanged some ideas. And those people are very humble, say we're still a whole lot more to learn. That's why we choose for everybody. Even those experts, there's still a whole lot more to learn. So really good starting point. And let's say pending from California, really difficult for you to wake up at 7:30 to go to a meeting. Thank you so much on that. Amin and Vinaya do a wonderful job on this. One thing I really quite impressed is we not only stick ourselves in statistical work, we're now talking to communicate with computer science people, learning what they're thinking and what they have. Instead, in the past, we just close our eyes, limit ourselves to the statistic. We don't talk to other people too well. That's something we need to change. And I see a big hope from this type of series. We starting to communicate with computer scientists, people, let them know us, let us know them as well, so we can speak their language. So I would really strongly encourage those people who do research, not only publish in top statistical journal, but also publish top computer science journal, for example, or other, to let them know what we're doing, to let them know statistician also can contribute in many ways. So that's something I'm really excited about the whole series. Thanks everybody, especially the committee led by Michael Chu and other people. Thank you so much for all this excellent program. I really have wonderful thing to say. Probably people are going to talk about this for another few months for sure. This wonderful series. And we all record all the lectures, so you can take a look some of the times. I'm super very proud of distributors to inform other people what Purdue is doing nowadays. And I really appreciate all your support, all your help. Thank you. Thank you.
Yeah. Yep. Thank you,
Thank you.
Dennis.
Important
Thank
thing,
you.
important thing you should say 3 times. So thank you again.
Yep. And so again, I want to emphasize thank you to our panelists, especially Plang, for your discussions and your time. And also thank you, Plang, for just posting the link as well to
Okay.
Gelman's review.
Thank you for the invitation.
Yep.
Yeah.
So I guess we can stop now.
So
and thanks
Penny,
to our
welcome,
audience as well.
Penny, you're welcome to visit sometime in the future.
Okay,
Give us
yes.
Sometimes. All right. Good.
Thank you.
I guarantee give a good time rather than 7:30 a.m.
Yep.
Thank you.
Okay.
Bye.
Thank you, everybody.
Okay.
Have a nice
Bye,
weekend.
bye, everyone.
Bye.
Yep. Bye, bye.